Hello everyone, welcome to the second lecture of Signals and Systems. In this video, we'll discuss about some useful signals and then we'll see what are called as the even and odd signals. So let's get started. First, let us look at what is called as a unit step function. So unit step function. We can also call it as signal. So in our discussion, since we are considering signals as mathematically it's a function, right? So we can say function and signal are synonymous. Okay? So it is represented as u of t. And it is defined as 0 for t less than 0 and 1 for t greater than or equal to 0. So if you try to see it graphically, what do you have? So t, you have u of t. For t less than 0, it is actually 0. And for t greater than or equal to 0, it is 1. Right? So it is like a step, correct? So, and it has a value of 1. So it is called as the unit step function. Okay? And if you also see, it is not continuous at t equal to 0. Right? So u of t is discontinuous at t equal to 0. So what do you mean by discontinuity? It is like if you approach the value from one side, it gives some other value as when you approach it from the other side. For example, from left hand side, u of t equal to 0 minus. So what is the value at this point? It is close to 0, right? And u of t, if you approach it from the right side, from the positive direction, you actually get the value of 1. So we say it is discontinuous at t equal to 0. But still we are stating at 0 itself it has a value, but still it is discontinuous. So it is possible, right? So for discontinuity, for continuity, the condition is u of 0 plus, let's say, or any at any t, right? So t plus is equal to u of t minus is equal to u of t. So if this condition is satisfied, then we say that function is continuous at t. But here, since it is not satisfied, we say the function is discontinuous. But still we are going ahead and defining the value of u of t at t equal to 0, which is 1. So this u of t is useful in many cases. For one case, if we were to consider, in the last lecture we saw what are causal signals. Causal signals. So these are signals which is 0, right? Signals which are 0 for t less than 0. If you see, this u of t also has that property. So if you take any signal, let's say x of t, and you multiply it with u of t, what will you get? What will this be? For t less than 0, it will be 0, right? And for t greater than or equal to 0, it will be x of t itself, because u of t is 1 there. So this, now even if x of t is non-causal, x of t into u of t, the multiplication is causal signal. So this is a causal signal. So u of t is useful in defining the causal signal. So one example if you have to see, so e power minus t, right? How does this look like in the graph? So at t equal to 0, it has the value 1. And as t is greater than 0, it decreases and goes to 0. And when t is negative, it actually increases exponentially. So now this is a non-causal signal. And its value actually is blowing up in the negative direction. Now we want to make it as causal. Then what do? We just multiply it, u of t. So for t less than 0, it actually is 0. And for t greater than 0, it follows this same curve. So it starts from 1 and goes to 0. Right? 1 year. So another use of this unit step function is in defining the function piecewise. So what do you mean piecewise? For example, if you want to, let's say, describe this function mathematically, a rectangular pulse, let's say from 0, 3 to 6 and t, and having value, let's say 4, right? Some function x1 of t is this. So I can define this function using unit step function. So how do I do that? So first I have the unit step function. So t, u of t. So it is like this. Now I can do a shifting operation on this signal, time shifting. So if I shift this to 3, then I have u of t minus 3, right? Then it starts from 3 and it goes on, right? And it's having value of 1 everywhere. And I can have u of t minus 6. So where will it start from? It will start from 6, right? So it will start from 6 and go on. And its amplitude is 1. Now if I just, this is u of t minus 6. Now if I just subtract these both signals, so this signal and this signal, what will I get? Okay, so I need to consider 3 regions, right? So let me consider 3 regions. So this is the first region. So t less than 3. So t less than 3, the first signal is 0 and the second signal is also 0. So their subtraction will give me 0 only. So this is 0. And between 3 and 6, the first signal is having amplitude 1 while the second signal is 0. So their difference will give me 1, 3 to 6. And if you see t greater than 6, both first and second signal is having amplitude of 1. So their difference will give me 0. So now if you see, you have got the structure. Only difference is the amplitude is different, right? So how do you represent this? This is u of t minus 3 minus u of t minus 6. And if you want to get amplitude of 4, what do? You just multiply it with 4, right? So we get 4 into u of t minus 3 minus u of t minus 6. So this will be now amplitude 4 starting from 3 and going to 6. So this function, this representation is actually telling me if I use this as a multiplication for other signals, let's say I have another signal x2 of t and I multiply that with this signal. So u of t minus 3 minus u of t minus 6. So it only takes the value of x2 of t in the interval t less than 3 less than t less than 6. Right? Only in this interval it considers the value of x2 of t. So this is called as piecewise definition. Piecewise definition. So if I have, let's say, some 2 functions, x1 of t, 2 signals x2 of t, and I want to create a third signal x3 of t such that it is x1 of t in the interval 0, t, 5, and it is x2 of t in the interval 5, t, 8. Then how do I define it? So x3 of t is equal to x1 of t into, so u of t minus u of t minus 5, correct? Plus x2 of t into u of t minus 5 minus u of t minus 8, right? So this is called as a piecewise function. And you're defining it piecewise in the time, from 0 to 5 separately and 5 to 8 separately. And they don't interact with each other, right? Similarly, you can also define anti-causal functions. So what are anti-causal function? They are 0 for t greater than 0, right? So then what do you do in that case? So you just can take the time reversal of u of t, which is u of minus t. So u of minus t will be like this. So it is 0 for t greater than 0 and 1 for t less than 0. So then any function you can take and multiply it with u of minus t. So this will give you an anti-causal function. Again, you can take the exponential function e power t. So how will e power t look like? So it will just increase, and at t equal to 0, it has a value of 1. Now if you want to make it anti-causal, then you take e power t u of minus t. So it will just come to 1 and then become 0. Correct? So if you are clear with this, next we will see about the unit impulse function. So unit impulse function, and it is represented with delta of t. It is the Greek symbol delta. So how do we define this function? So we define it this way. So delta of t is nothing but 0 for t not equal to 0, and it actually tends to infinity for t equal to 0. So graphically, how do we represent it as? This way. So if this is t and this is delta of t, we represent it with a single line at t equal to 0 and followed by an arrow. So this indicates that at t equal to 0, it is actually tending to infinity. And this infinity is actually not defined. It is equivalent to saying that the impulse function is not defined at t equal to 0. And how do they actually define this function is, they define it by saying delta of t is equal to 0 for t not equal to 0 and integral delta of t dt from minus infinity to infinity is equal to 1. So what does this second statement mean? It means the area under the unit impulse, right, delta of t across all time is equal to 1. So that means the area under only this part, right, is equal to 1. So graphically, how do they picturize this is? So if you have a, let's say, a rectangular waveform, okay, with from time epsilon by 2, from minus epsilon by 2 to epsilon by 2, and its amplitude is epsilon, right? And you let amplitude is 1 by epsilon. So what is the area under this rectangular pulse? It is base into height, right? So which is epsilon into 1 by epsilon, which is nothing but 1. Now what you do is, you tend epsilon to 0, right? You reduce the value of epsilon closer to 0, right? So then what happens? This width actually shrinks, right? This width is shrinking. And what happens to the height? Height is growing up rapidly, correct? So when actually epsilon tends to 0, then it becomes, so this width itself tends to 0, right? And the height tends to infinity, correct? So then you have a impulse. This is what we have defined mathematically before, correct? Delta of t. But if you ask me, in reality, do we actually have these kind of signals? No, right? In reality, all signals are going to be continuous, and nowhere it will go to infinity. But these signals are required for us for mathematical analysis, which we'll see in the later parts of this lecture series. So it is required for us to define this beforehand. And you should also get familiar with these types of signals, at least the unit step function and the unit impulse function. And this is not the only way to see how this impulse response is forming. You can also take a triangular signal. So for triangular signal, what do you have? Okay, you consider from minus epsilon to epsilon. And the height you take as 1 by epsilon. Now the base is 2 epsilon, right? The width of the base is 2 epsilon. So half into 2 epsilon into height, 1 by epsilon. So 2 cancels, epsilon cancels. So this area is also 1. So again, what another fact I missed to say is the area is not dependent on epsilon. So even whatever value of epsilon you take, the area is going to be same. And then you are tending epsilon to 0. So the area is going to remain same and it is going to be 1 itself. Right? So here also if you see, the area is not depending on epsilon. And now if you tend epsilon to 0, the base will shrink to 0 and the height will blow up to infinity. Right? So now we'll see some properties of this impulse response. Properties of impulse or unit impulse, right? Unit impulse function or signal. And what does the word unit means? Unit means the area is 1, right? So if you have some k delta of t, this is impulse with value area k. Impulse with area k units, right? So first thing is multiplication property. Okay, so if you take any signal, any other signal x of t, and you multiply it with delta of t, so what do you think will we get? So if you again take, okay, let me take some function x of t, and the delta of t is something like this, right? So if you see, when you multiply at every other place except t equal to 0, it is going to vanish. This function is going to vanish. And only at x equal to 0, it is going to hold the value. And at that point, it is going to be infinity. So it is equivalent to saying it as x of 0 delta of t. Correct? This holds. Now, you can also shift the impulse, right? T minus t naught. So in that case, what will you get? So if you shift it, then what will this delta of t minus t naught look like? So this impulse will actually come at the point t naught. So then what will be the function value that remains? It will be x of t naught. So this will be equal to x of t naught delta of t minus t naught. So the information of the signal at all other points is removed except where the impulse actually is present. Correct? Again, if you want to multiply it with other impulses, right, having area greater than 1 or different than 1, right, then you can just say x of t into k delta of t. So it will be the same. So it will be k into x of 0 into delta of t. Similarly for this case also. Okay. So the second property is really useful. It is called as the sampling property. Okay. So now you have multiplied. Now what happens when you integrate this product? So integral minus infinity to infinity x of t delta of t dt. So what happens to this value? Okay, first we already found what this multiplication is. So it is x of 0 delta of t into dt. And then what happens? So this x of 0 is just a single value. It is going to be a constant. It does not depend on time. So we can take it out. So x of 0 integral minus infinity to infinity delta of t dt. But what is this? This is the area under the impulse, which is nothing but 1 here, correct? Because it is an unit impulse. So it is x of 0 into 1, which is nothing but x of 0 itself. So it is like equivalent to sampling x of t at t equal to 0, right? You actually get the value of x of t at t equal to 0. Suppose you want to get the value of x of t at t equal to some t naught. What do you do then? Exactly. So minus infinity to infinity, x of t, delta of t minus t naught into dt. So this will actually give you the value of x of t at t equal to t naught. So this property of the impulse response or the impulse function is called as the sampling or shifting property. So next, if you see, there is a beautiful relation between this impulse function, unit impulse function, and the unit step function. So we'll take a look at it. Relation between unit impulse and unit step functions. So you have the unit impulse delta of t. And what is the unit step? So it is going to be 1 here, t, u of t. So now if you just take delta of t dt and integrate it from minus infinity to just t, right? Now you are giving t as a variable itself. So now what happens? Okay, so for t less than 0, let's say, t less than 0. So then you are integrating from minus infinity to some t here. So what will be the value? It is 0, correct? So it is going to be 0. Okay, for t greater than 0, what do you have? So here, so now this part itself is coming into the picture. So the area is obviously going to be 1, correct? But actually this is actually the definition of the unit step function. And we know that it is not defined at t equal to 0. And we have only taken the value at that t equal to 0, it is 1. So here also the integral itself is not defined at t equal to 0. Because this function is discontinuous and it is also blowing up. So we can define at t equal to 0, it is actually 1. So then, what is the unit step function? U of t is nothing but integral minus infinity to t delta of t dt. So u of t is nothing but the integral of the unit impulse function. On the other hand, the unit impulse function is nothing but the derivative of the impulse response. Derivative of the unit step function, right? So if you have this, the derivative here, it is not changing. So the derivative will be 0. And at t greater than 0 also, it is not changing. So the derivative is again 0. But if you see here, there is a discontinuity. So the derivative is going to blow up at the discontinuity, which is nothing but the impulse function, right? So these two are very important definitions. So firstly, we had delta of t, then we integrated it and we got u of t. And now let's say we integrate u of t also. What will we get? So integral u of t dt minus infinity to t. Again, for t less than 0, it is going to be 0. And for t greater than or equal to 0, it is going to be, this is going to be 1. So the integral will be t. So we'll have something like this. Correct? So this is t. So this is called as a Ram function. I will denote it by r of t. So r of t is nothing but t into u of t, right? Because it is 0 for t less than 0 and it has only value for t greater than or equal to 0. And you can see it is ramping up, so it is called as a ramp function. So this is all about the unit impulse and unit step functions, and we'll be using it in the next lectures and so on. So next we'll see about the exponential function. So complex exponential. So we denote this by e power st, and s is complex, a complex number. So this function itself is some f of t is e power st. And if s is complex, then we can write it in terms of two real numbers, sigma plus j omega. So this is the real part, and this is the complex part, or the imaginary part, right? Imaginary. And then what does f of t become then? E power sigma plus j omega into t. And you can multiply, you will get it as e power sigma t into e power j omega t. And you have the Euler's relation or Euler's formula. So e power j x is nothing but cos x plus j sin x. So it is actually related to the cosines and sines, right? So this actually comes from the Taylor expansion. So if you have the exponential, the Taylor expansion is something like 1 plus x square by 2 factorial, x cube by 3 factorial, and so on. This is the Taylor expansion, right? Similarly, for sin x, what do you have? You have x minus x cube by 3 factorial plus x power 5 by 5 factorial minus and so on. And cos x, you have 1 minus x square by 2 factorial plus x power 4 by 4 factorial and so on. Now if you just take e power x and substitute some j omega instead of x, then what do you have? 1 plus j omega, right? Plus j omega square by 2 factorial plus j omega whole cube by 3 factorial and so on. So now you know j square is equal to minus 1. So if you write it in terms of that, you have 1 plus j omega minus omega square by 2 factorial, and you have 1 minus and j omega itself, omega cube by 3 factorial and so on. So now if you collect all the real terms and imaginary terms, you have 1 minus omega square by 2 factorial plus you will get omega power 4 term by 4 factorial and so on, plus j into this omega minus omega cube by 3 factorial and so on. But what is this? This is nothing but sin omega, right? Sorry, cos omega, correct? Plus j into, this is nothing but sin omega, sin omega. So this is the Euler's formula or Euler's relation. Okay. So then using that for this f of t, what do we have? So then we'll have f of t is equal to e power sigma t into cos omega t, right? Because it is j omega t. So cos omega t plus j sin omega t. Okay. And if you want to define other things like complex conjugate of f of t. So you can define it by f star of t, and it will be e power sigma t. This will not change because it is the real part. Omega t minus j sin omega t, right? Only the imaginary part will have a minus sign. And if you want to get only the real part from this, what do you have? So let's say I want only the e power sigma t cos omega t term. Then I just add these two and divide by 2, correct? So f of t plus f star of t by 2. And f of t itself is nothing but e power st. So this is e power st plus e power s star of t by t sin omega t. And what about the imaginary part? What should I do? E power 6. So I should subtract f of t minus f star of t and divide by 2j, right? So it is e power st minus e power S star t by 2j. So, okay, now we have defined it, but how does it look on the graph, right? So, it is not straightforward because you will need 3 axes to represent this one function. So, one you need for the amplitude, let's say one for the real axis and one for the imaginary. So, it is not straightforward to see it graphically on a 2D paper, but you can just separately plot the amplitude versus the real, and then the second one you can plot amplitude versus the imaginary axis, right? So we'll go ahead and see that. So we have f of t is equal to e power st is equal to e power sigma t into cos omega t plus j sin omega t. Now let's see the real part. So let's, for first simplicity, let's take omega equal to 0, right? Then what happens to this? It just becomes e power sigma t. It is nothing but the simple exponential function. Simple exponential function, right? And how does it look like? For sigma equal to 0, okay, I'll plot it here. Sigma equal to 0, it is just equal to 1. It is a constant function, okay? And for sigma greater than 0, it is a growing function. And at t equal to 0, it is 1. And for sigma less than 0, it is an exponentially decaying function. And it decays to 0, right? Okay. So this is for omega equal to 0 case. Now let's say omega is not 0. What happens then? So then you will have this real and imaginary problem. So real part, what do I have? Cos omega t. This is real. And imaginary, what do I have? E power sigma t sin omega t. Correct? Okay. Now I have these again. For sigma equal to 0, it is just cos omega t. So it will be like this. And goes from 1 to minus 1. Right? And then for sigma less than 0, it will be an exponentially decaying sinusoid. So let's take sigma less than 0. Let's say this is the e power sigma t for sigma less than 0. And the minus invert case, it will be something like this. It will pass through minus 1. So how will the sinusoid look like? So it will just be an amplified version. Here it will be same. And then it will start to shrink. Right? It exponentially decays. Right? Maybe it will be better if I draw it separately. Correct? Okay. So I'll copy this. Okay. So now I have 1 and a minus 1 and this exponentially decaying signal. And the sinusoid will be, cos will be actually like this. Right? And what about sigma greater than 0? It will be the opposite of this. So sigma greater than 0, 1 and minus 1, it will be growing function. So we'll have something like this. Right? And what about the sine case? It is the same, just that it will be phase shifted to represent a sine. So this is the real part actually, and the imaginary part. Let's take it down. So the initial signals will be same. So for sigma equal to 0, so it will just be between 1 and -1. And it is a sine, so it will start from 0. And what happens to the other case? For sigma less than 0, it is actually a decaying function. And then you have sine. And for sigma greater than 0, you have an exponentially growing function. So it will be in these limits. Okay. So you can also define this function in what is called as a complex frequency plane. So this omega sigma is like some oscillations, right? It is having some frequency. Omega is nothing but a radial frequency or the angular frequency. So f of t is e power sigma t into cos omega t plus j sin omega t. And it is nothing but e power st. And this s is the complex one, the sigma plus j omega. So this x is called as the complex frequency. So omega is something like the imaginary frequency, right? Imaginary part of the complex frequency. And I can have a frequency plane, complex frequency plane. So this axis will be the imaginary part of S. So this is nothing but omega, and this is real part of S, nothing but sigma. So if I want S is like 2 plus J3, nothing but here 2 here and 3 here, this point, right? 2, 3. So what kind of signal will you get for it? So since this real part is greater than 0, you will get an exponentially growing function. Exponentially growing function. Right? So whatever is there in this part, it will be exponentially growing function. And whatever is there in this part will be a exponentially decaying function. Correct? So this is actually called as the left half plane. And this is called as the right half plane. So these definitions will be useful for you in the control signals point of view, and even for our case it will be useful when we define some integrals. So we'll see that later on. Now for now you can just take these as given. So that is all with the complex exponential functions. So next we'll go ahead and see about even and odd functions. So we define an even function. Xc of t this way, right? If it is symmetrical about the vertical axis, right? And mathematically it is nothing but xc of t is equal to xc of minus t, because the minus t is nothing but the time reversal which shows the reflection about the vertical axis. And if the signal is symmetrical, so then xc of t will be equal to xc of minus t. So for example, whatever is there here, the same thing should be present here also. So then it is called an even function. An odd function is just opposite of it. An odd function is xo of t if it is antisymmetrical about the vertical axis. So what is antisymmetrical is nothing but xo of t is equal to minus xo of minus t. So whatever is the signal here, which should actually be reflected, let's say it's reflected, and it is the negative of that, right? It's negative of that. Okay. So it is also like saying it is a reflection about this 45-degree diagonal. So whatever is here will be here. Or on the other hand, it is like saying you first take the reflection on the vertical axis, then you do the reflection on the horizontal axis. Both are synonymous. So this is called as an odd function. And as examples, if you see the cosine function, cos t, it is something like this. Right? You can see the reflection is perfect. Correct? So it is an even function. On the other hand, if you take a sine function, sine t, then what do you have? You have this side, and this side it actually goes like this. If you see whatever is going this side, it is actually going in the negative direction in the other side. Correct? And everywhere. So it is an odd function. Okay. Another example, if you want, you have mod x or mod t. Mod t, how does it have? It's like this, right? So both sides are symmetrical. And it should be symmetric everywhere, not just in a particular place, right? Not just say -1 to 1. Not just here. It should be in the entire range from 0 to infinity and 0 to minus infinity. And this side you have the t itself. So it is like this. Here it is 0. You can see this is antisymmetric and it is an odd function. So let us see some properties of these functions. Properties. So we'll see what happens when we multiply these functions, right? So we have an even function and we multiply with an odd function. So what can you say about the resulting function, right? xc of t into x o of t. Let's say this is some function f of t. So what can I say about the resulting function? So we'll just check what is f of minus t. And then from that we'll try to deduce, right? So it will be xc of minus t into xo of minus t. But xc of minus t is equal to xc of t because it is even. And xo of minus t is equal to minus xo of t because it is odd. The 1 minus sign only it comes into xc of t into xo of t. And this is nothing but the f of t itself function. So minus f of t. So f of minus t is equal to minus f of t. So what is this function? It is an odd function, right? So similarly, you can derive for others also. So even function into even function. What is it going to be? So from here plus 1, from here plus 1. So it is going to remain plus 1. So it is again an even function. Similarly, odd function, multiply with an odd function. Minus 1 from here, minus 1 from here, it gives you plus 1. So it is an even function. So another property is finding the area. So if I want to find the area of an even function, xc of t dt, I know that it is going to be same from minus infinity to 0 and 0 to infinity, correct? So I can divide it into two parts, xc of t dt plus 0 to infinity xc of t dt. But these are literally the same functions. So I can just write it as 2 integral 0 to infinity xc of t dt. It is just sufficient for me to compute the integral from 0 to infinity, right? And what about the odd function? X of t dt. What about this? Okay, I have minus infinity to 0 xo of t dt plus integral 0 to infinity xo of t dt. So these are again same, but just for a minus sign in this case, negative sign, correct? So whatever area comes here, it is going to be negative in this case. So these both actually cancel out and we get 0. So if you want a rigorous proof, you can just do a change of variable here from t to minus t. Then this integral will actually go from infinity to 0. You will get x0 of minus t and dt will become minus dt. So this minus sign will take care of the reversal of the integrals 0 to infinity xo of minus t dt. And this will remain same. But xo of minus t is nothing but minus xo of t. So this is minus 0 to infinity xo of t dt plus xo of t dt from 0 to infinity. And if you see, these are going to get cancelled. So same way for this, they will just add up, right? So this is with even and odd signals. And in general, any signal, if you take any signal, let's consider phi of t. So it can be composed into an even component and an odd component. So any signal phi of t can be composed as a sum of an even signal phi e of t and an odd signal phi o of t. It's very surprising, right? So let us see how. So I will define phi e of t like this. It is actually phi of t plus phi of minus t by 2. Okay. So now if I try to see phi of minus t, what will I get? I'll get phi of minus t plus phi of t by 2. This is nothing but phi e of t itself. So this is an even signal, right? And for odd signal, what do? I just take phi of t minus phi of minus t by 2. Now if you take, you will get a negative sign extra. Then it will be an odd function, correct? If you want to quickly see it. So phi of minus t minus phi of t by 2. So this is nothing but minus phi o of t. So this is an odd function. Now if you try to add this and this, so phi e of t plus phi o of t. The second term is going to cancel and the first term is going to add up, right? Sorry, this and this, right? This is, sorry, minus t here, right? And if you just take sum of these two, what will you end up? The second term is going to get cancelled and the first term is going to add up and you will get phi of t. So this is what we wanted to prove, right? So any signal phi of t can be decomposed into a sum of an even signal and an odd signal. So you can also define a function like this, even of x phi of t. So this is nothing but phi of t plus phi of minus t by 2. And another function is odd of phi of t. This is phi of t minus phi of minus t by 2. Okay. And for the complex parts, right, these are all real signals. For the complex signals, we have something called as the conjugate symmetry. Conjugate symmetric and conjugate antisymmetric. So what is conjugate symmetric? So x of minus t or x of t is equal to x star of minus t. So it is the complex conjugate of minus t, right? So if I actually compose x of t as some a of t plus j b of t, what will this be? This will be a of t plus j b of t is equal to a of minus t minus j b of minus t. And the real part should be equal and the imaginary part should be equal. So it means a of t is equal to a of minus t and b of t is equal to minus b of minus t. So conjugate symmetric, what it means is it is even in real part and it is odd in imaginary part. Right? And then you have what is called as a conjugate antisymmetry. Conjugate antisymmetric. So this will just be opposite. So you have x of t is equal to minus x star of minus t. So here what do you have? A of t plus j b of t is equal to minus a of minus t plus j b of minus t. So equating the real parts, I get a of t is equal to minus a of minus t and b of t is equal to b of minus t. So what is this? This is odd in real part and even in imaginary part. Correct? And similarly, like what did we decompose this phi of t, right? Okay, this I'll write as decomposed. Same way we can decompose any complex signal x of t into two parts. One is the conjugate symmetric part and the other is the conjugate antisymmetric part. Alright, and how do you define it? So xcs of t is nothing but x of t plus x star of minus t by 2 and xca of t is nothing but x of t minus x star of minus t by 2. And you can try to actually verify this if this is actually conjugate symmetric and this is conjugate antisymmetric. And their sum actually is straightforward that it gives x of t. So until now we have covered all the important parts in the signals, and from the next lecture we'll start with the systems. Kindly go back and read from the books and also practice some questions because you know a few concepts in this. Great. Have a nice day.